Hi everyone. Today I'm gonna present my poster Domain Adaptive Transfer Learning on Visual Attention Aware Data Augmentation for Fine-Grained Visual Categorization. I'm Ashik Imran. I'm a PhD candidate in the Department of Computer Science and Engineering, University of Texas at Arlington. So fine-grained visual categorization is a challenging topic in the field of computer vision. So the main challenge is it has large interclass differences and subtle interclass differences. So there are significant interclass differences among subcategories, and items from different classes may look very similar. So the examples of FGVCs are like species of birds or dogs, or different types of foods or flowers or cars or aircrafts. And the main problem is FGVC datasets are not very big, so it is very critical to design methods that can compensate for the limited amount of the data. Some of the examples of FGVCs are shown here, that the aircraft images, some bird images. So bird images include the different species of bird, uh, and you have to recognize the correct species of birds efficiently. Then examples of cars, you have different brands of cars, but to specifically recognize the which brand of the car it is very challenging. So our main contribution of this poster was we propose a simple yet effective improvement of recently proposed baseline method WSDN, which has been used for generating attention maps to extract sequential local features to tackle the LGV's challenge. And we used a domain similarity score that can be played a vital role before applying transfer learning on the you on this domain. Then after, we can employ the weekly supervised data augmentation network to achieve better results among FGVC datasets. And we demonstrate a domain adaptive transfer learning approach that combines with the visual attention data augmentation uh, uh, technique, and we can achieve state-of-the-art results on various FGVC datasets. So we present the relationship of top 1 accuracies and domain score on 6 commonly used FGVC datasets. We illustrate the effect of image decision in transfer learning in detail. So for let me clarify what are the source and target domains for domain transfer learning. So source domain include here the large scale data set. Typically we have ImageNet. So but for our case, we also use iNaturalist. So iNaturalist is a also a very big data set that includes mostly the nature oriented classes, like including birds, including trees, lot of things. And target are the FGVC datasets. For our experiment, I used flowers, food, bird dataset, aircraft, dogs, and cats datasets. So let's see what the domain adapted transfer learning is. So first of all, as I mentioned, FGVC datasets are not very big, so it is very difficult, also critical to design methods that can compensate the limited amount of data. So we can do fine-tune a network, and there are two ways to do that. You can use typically you need two domains to do that. So you have a source domain that is typically contains a large scale data set, and you have a target domain. So basically you are transferring knowledge from your source domain to the target domain, and that can help to boost the accuracy number for the target domain. So we propose the technique that allows the model to learn features more effectively and perform well on large scale fine-grained data sets. So in order to calculate the domain similarity score, use odd mover distance. So this distance method has been uh, provide very effective results so far. And using this distance, we actually know that which target domain is good for which source domain. So these are the networks of our experiment. That so we have input image, and then we use feature extraction. So main thing is we are using attention maps for data augmentation. So since the data are not that big, so we are using data augmentation technique, and data augmentation technique are using attention maps. So attention maps are using as a data augmentation, and the data are actually coming back to the input image, and in order to get more data, we are using that. So this is the training stage, and this is the testing stage, that you are using that the additional data augmented data, and then you are passing through it, and we are generating the part matrix here. So some visualizations of WSDN here, that so basically uh, from the left to right. So left is the visual attention of image. So visual attention means that it actually uh, like uh, takes the most important features out from particular image. Then we are actually showing the attention maps on the right, then we're showing the feature maps, that and in the later we are doing the attention cropping, that we are using most important feature of that particular image and using as a data augment, using that part as a data augmentation. Here we are using attention dropping. So basically what we did for attention cropping, we won't repeat that particular region of an image. So we are actually discarding that here. So so that that cannot be, we won't repeat that particular region. So this is for flower dataset, the same thing happened. So as you can see that attention dropping is happened here, that so we won't use it for the next iteration. And this is for attention cropping. So these are the experiment, the dataset size that we have imagined, that has 1,000 classes and more than 1 million training images, and test 50,000 test images. So initially is another large scale dataset that has 5,000 classes, about over 600,000 training images and 10,000 test images. And these are the targets. I mean, as you can see, there are not much data sets here. So these are the results that we got compared to the previous existing methods. So for our technique actually showed state of the art result, 5 out of 6 data sets. Uh, and this is how we vary our learning rate for our experiment. And this is the top one accuracy that we got for the BART dataset, is 91.2. That is the highest so far in this domain. And we also analyze the effect of transfer learning on different sizes of image resolutions on IGS. So basically we want to prove that if we use a large scale larger size image for the source domain, that will give better top on accuracy when we do the transfer learning. And this is the most like the correlation between the top one accuracy and domain score that we calculated for source and target domain. So the straight lines are showing are the FGVC datasets, and the pointers like the green diamond and the red cross and yellow triangle, those are the large scale datasets. So as you can see that it is kind of positively correlated to the for top on accuracy and domain score. So if you have more domain score, it tends to get more accuracy for from source large scale dataset to the FGVC dataset. So so it describes a simple technique that takes the attention mechanism as data augmentation, and the attention maps are guided to focus on the object's part and encourage multiple attention. And we demonstrate Adobe Representation plays a vital role boosting accuracy of FGVC datasets. And we show that combining domain similarity score with attention-based data augmentation technique can achieve state-of-the-art on multiple FGVC datasets. And we also analyze the effect of the image resolution on transfer learning between the source and the target domain. Thank you so much.